Week 2, lesson 4. This is how to find the volume of a parallelepiped using this formula. A couple things to notice on this thing. There's both the cross product in here along with the dot product in here, and these are absolute value bars, all right? Because there's going to be times when you do this computation and you will get negatives. Just make sure you end up with a positive because volumes do need to be positive. Now, something again to recognize, the stuff that's underlined in blue results in a vector. Once you have that vector and you do the dot product with part C, you end up with a number, right? Cross product results in a vector, but the dot product results in a number. All right, so let's jump right on in. Let me scoot it up a little. Maybe make it a little bit bigger. Okay, so it says, find the volume of the parallelepiped enclosed by A, B, and C. So I am going to do the cross product with A and B. I, J, K. A is -1, 1, and -2. And B is 2, 1, -3. I minus J plus K. All right, so again, expansion by minors should give me -3 plus 2. Here, 3 plus 4. And lastly, -1 minus 2. That means my resultant vector is -1, -7, -3. Now I have to do the dot product with the one vector that I haven't used yet, which is vector C. 1, -2, 1. And if you remember, I'm going to multiply these two together. I'm going to add to that these two multiplied together. And I'm going to add to that these two multiplied together, which equals 10. If I had to, I would take the absolute value in order to make that positive, but it's already positive, so that is the volume. Okay, now here's another kind of cool thing. There's a way to tell if vectors are coplanar, meaning that they lie on the same plane. And the way to do that is if you have a volume of a parallelepiped that equals 0, all right, which means all three of those vectors lie on the same plane. It doesn't make a three-dimensional object. It just makes three different vectors all lying on the same plane. So I'm going to do the exact same thing I just did. I'm going to, whoa, that's not good. There we go. I'm going to do the dot product with A and B, which would be vector, let's see, 1, -2, -4, and for B, -1, 1. Expansion by minors will become sort of second nature after doing all these problems. So this becomes -2 plus 4, for J, 1 minus 4, and for K, 1 minus 2. So my resultant vector is 2, 3, -1. That is perpendicular to both A and B. And then let's do the dot product with C. It's the one vector I haven't used yet. 2, -1, 1. So doing that dot product, I get 4 minus 3 minus 1, which does equal 0. So yes, these are coplanar.